Bienvenidos and welcome to our 5th video tutorial. Wow, can you believe it's already a 5th tutorial? Oh, well, today I'm going to be talking to you a little bit about the essentials of connection design. So, where do we begin with connection design? Oh, you're probably dreading this. It's actually not so bad. Actually, it kind of is, but not really. Anyways, so the first thing you'll want to do is, of course, refer to the rules. I just kind of looked through here, and the first thing that you want to check is it should be fasteners, and you can find this under material and component specifications. So there are a couple rules on fasteners. These will probably stay the same. They might change a little bit, but essentially the main restriction is that your bolt diameters have to be at least 3/8 inch, and you have to have a nominal length of 1.5 inches for the length of the bolt. So I've gone ahead and taken the liberty of drawing, and I say drawing, but I actually didn't draw these. I found a delightful resource online where I was able to pretty much just download these. Somebody had already drawn them up, and I just kind of borrowed them. So you can find things like this. They're really nice, and these are all kind of blocked up, so you can move them around and junk like that. So we'll be using these to visualize some of the concepts of connection design as we proceed forward. So let's first take a look at an example. Here is our bolt, and I've threaded our nut, I guess, onto here, and here's kind of a side view of the bolt, as if we were looking from the top down on the bolt. That's kind of this perspective. This is more from the side, I guess you might think. So where do we begin? Well, one place would be to come up with some kind of male connection. Now, there's a whole bunch of places you could start with a male connection, but I'm going to look at just double shear connections for now. The most simple connection you could probably think of. So here's an example of what a single male part might look like. Now, the main components you can see are just kind of this region here that kind of juts out, and that's basically where you have a hole that drills through. And I'll kind of unhighlight my box here so you can see. Looking through here, I have the dashed lines to represent where the hole will go through the main male part, and then I have these little kind of details just to show where maybe I might chamfer these edges with, say, one of those conical shaped deburring tools. So I've included a chamfer of about maybe 1/32. I don't know, it's just a guess. Really, right now I'm just kind of trying to get out some ideas. So the main idea here is using our knowledge of what our main constraints are dimensionally. So how do we control, say, this dimension? How do we design for that? Well, it's actually not too bad, and I'll throw in the female part here to illustrate the main limitation here, and that would be milling the female connection. So of course, if you're going to mill your male connection, all you have to do is cut out these areas on these sides, and then you pretty much just have this thing that you can do a drill press through. However, on the female connection, you have to cut out this whole inside area here, as well as on the outsides. So cutting through the center area can be quite a limitation, especially considering the fact that you're trying to pretty much get an end mill to go all the way through this thing. You don't want to be using really, really small sized end mills, and I'll kind of illustrate some of the main sizes of end mills that you might encounter. So I'll throw in my dimensions just to illustrate these a little better. So here's an array of probably the most common end mill sizes that you would probably find. These are all diameters. So starting from the smallest, I did at one point use 1/8 inch end mills, but I highly regretted it, and I would highly advise that you don't pursue any designs that make need of 1/8 inch end mills, because you will be losing a lot of money doing it. So try to avoid it. I'd say probably a good size to go with as a minimum is about 1/4 inch. That's just, it's a decent size. You can get roughing end mills in 1/4 inch diameters. It's just kind of a nice small dimension. And in fact, that's precisely what I have as this dimension here. And as you can see, I'm using that dimension of 1/4 inch to dictate pretty much the width of this cutout on the female. So that also dictates pretty much the width of the male part. Simple as that. So already, we've got our dimensions kind of falling into place just because we know, well, our end mills are going to limit how, I guess, how big this space in the female can really be. Now, if you're using single shear connections, then I guess that's not a limitation, but I don't think we really want to do that unless it's something that doesn't take a whole lot of load. So, now the next thing would be, well, okay, what do we want the width of these wings on the female to be? Now, a good criteria I like to use is just simply cut whatever the diameter or the thickness of the male part is in half, because really you're trying to obtain the same basic cross-sectional area. So if the male has 1/4 inch by whatever the depth is, I guess in this case it's 5/8 inch, then in order to match that area on the female, then all we have to do is just say, okay, we'll make each wing 1/8 inch, or half the thickness of the male. So easy, really easy. Now all we have to do is kind of come up with, well, how much do we want these little overlap things, how much clearance do we want pretty much on the outsides of these. Kind of taking a look in this perspective. So here we're looking through the whole of the connection. I have the female part here, and here's a lip on the male, here's the lip on the female, and so on. So here's a dashed line just to show the end of the male piece. So how do we decide what this dimension should be, here to here? Well, there's probably a number of ways that you could do this. One way would be to reference some of the notes from your trusty steel design class for bolt design. And as you probably recall, there's two main failure modes for bolts, one being bearing and the other being tearing. So you could use some of your design equations from that to get some rough estimates of how much you would want this dimension to be, and likewise how much you would probably want this dimension to be, possibly. You could even do maybe some rough kind of calculation of net section for these areas, and then kind of do a calculation kind of like that. Really whatever you want. But I would still suggest, even if you were to do those kind of calculations, either two, although I would suggest doing both, but either basically testing it in SolidWorks, creating a 3D model of your connection and testing it there, or milling out a prototype connection and then testing in real life. Again, I would suggest doing both of these because for various reasons the models in SolidWorks aren't going to reproduce the results of the real world with very great fidelity. So I would really suggest maybe distrusting SolidWorks. It's not the best finite element program, but it works. So it's SolidWorks. So now we know more or less what these should be, and I've just kind of chosen some kind of characteristic length scale or dimension. In this case, I'm borrowing this 1/8 inch thickness on our female wing, and I'm using that to inform, okay, well, I'll just make this clearance 1/8 inch, and likewise, I'll make this clearance 1/8 of an inch. Easy peasy. So now we have a kind of nice square box, and you can see this is actually exactly square. So in the event that maybe there's some shear going through the connection, or if it's in tension or compression or whatever, it'll be a pretty good, all-purpose connection, I guess. So very widely usable. Now, the other dimension that you might be worried about would be, well, how much do we want this full distance to be? Right here it's 15/16, but how did I come up with that? Now, you can kind of come up with a couple different criteria. Obviously, you need enough room for the bolt to fit. So, clearly you can see, alright, my bolt's fitting fine. But there's one other thing that you need to consider, and that is a socket wrench. You have to wrench these bolts together. That's, evident from this most recent year. Just being able to tighten up our bolts is critical. So making sure that you can get a socket wrench in here is the key. So I've gone and looked up the typical dimension for and this is for again, and I'll just kind of borrow here just to illustrate. Yep, this is for a 3/8 inch diameter bolt. So this socket wrench basically has a nominal diameter of, I think it's technically 14 millimeters or somewhere in that ballpark. I just said 0.87 inches. So borrowing that over and just kind of plopping it on here, you can see I have, a decent little amount of clearance to make sure that I can get my socket wrench in here so it's not going to be interfering with these lips on the bases of the connections. So that's how you might, ensure that essentially these distances are going to be spacious enough so you can wrench it. And then the last thing, of course, is how thick do you make your lip and how wide do you make your base, I guess. Well, both of those things might depend on a couple things. First of all, this dimension, I have it 5/8 here, and likewise it's 5/8 here, would probably depend on the original bar from which you were cutting out these elements. So I would say, if you had a 5/8 by 5/8 square bar, and I definitely would recommend a cold rolled bar just because it's, work hardened, so it's a little bit tougher. If you go with if you could find an 5/8 by 5/8 bar, that would be basically perfect for these kind of connections. So you usually want to keep them within some kind of dimension that feels characteristic. So 5/8 sounds like a good round number. Now, as for the lip width, this would be your personal preference, but I would suggest maybe even conducting some tests for welding purposes. So definitely you want to have a thick enough base such that when you weld this base onto a tube, then you're not going to be warping your connection. And that's especially dangerous if you're considering welding on a female connection. Because if you welded here and here, say, and the base plate was really thin, and then both of these female wings could really easily just start bending around and stuff, and that's not what you want. So a thick enough base to prevent bending and to isolate the rest of the connection from the welds, and have enough material to actually weld on. Also, there's some minor considerations with shear transfer of the load from these lips down to the edges of the tube, but we'll not get into it. You'll probably see that effect once we start modeling in SolidWorks. So essentially that's more or less it. Those are the major design considerations that you'd probably encounter if you were trying to create your own connections. But hopefully we'll continue looking at connections a little bit more in some future lessons. But in the meantime, go ahead and take a look at this file. I'll try to upload it, and maybe you can even start playing around and trying to come up with your own connections or different connection ideas, now that you know some of the main limitations of the design of the connections. Alright, so until next time, I wish you luck, and I will see you later.